Welcome to the first lecture of this week in EE557. In the last lecture we have completed the asymptotics of the mean and covariance of these linear Gaussian systems, and in this lecture we are going to see the last topic in the chapter that we are trying to cover in the book, and that last topic is Gauss-Markov processes. Well, our title is Gauss-Markov processes. We are going to immediately start by making the definition of a Gauss-Markov process. Let us say definition. A stochastic process. We are going to show this process with xk, and each of these xk are in Rn, and for k larger than or equal to 0 is said to be Gauss-Markov. We are going to abbreviate this with the letters, capital letters Gn, if and only if it is Gaussian. And what does that mean? Any joint distribution of these sequence elements here would be Gaussian. Well, in other words, for every k, the joint PDF of x0, x1 going until xk is Gaussian. That is what being a Gaussian process means. If it is Gaussian, and there is an explanation of this, and it is also Markov, meaning that, let us write its explanation as well, P of xk plus 1 given x0k is equal to P of xk plus 1 given xk. So we are saying that the Gauss-Markov process is a process in which these two properties, Gaussianity and Markovness, are there together. All right? And Gaussianity means that these x0 to xk are Gaussian for every k. The PDF of these elements here are Gaussian, and so these are jointly Gaussian for every k. And the second property is that we have a Markov process. And here we show the Markovness like this, only by using the one-step transition. That is actually going to be one of the questions that I would like to ask first. So remember, I have defined the property of Markovianness by the fact that m-step transition distributions having the Markov property. But here we define the Markovness by using only the one-step transition PDF. So why is this the case? We are going to see the answer, but let us first ask the question. Why do we show the Markov property using only one-step transition PDF? That is our question. And the answer is actually quite simple. The answer is that here in this stochastic process we really do not have the input, okay? And we are actually going to see that actually this is going to be sufficient for all m-step transition PDFs to be Markov. So this is going to be actually, we are going to see the answer that this one-step transition PDF having the Markov property is going to be actually sufficient for the m-step transition PDF to have the same property. So we are going to actually see that if I have this property, if I have this property, P of xk plus 1 given xk, then we are going to see that this implies P of xk plus 1, xk plus m given x0k is equal to P of xk plus m given xk only. Okay? This is because we don't have any input. We have just a pure stochastic process without any input or with any feedback. Okay? So when we have only a single stochastic process without any input in the given conditions, we can actually prove such a property. This is actually the case when we have an input, but the input is deterministic as well. All right? So when we have an input, and if the input is deterministic, this property would hold as well. So one-step transition PDF having the Markov property implies that m-step transition PDF having the Markov property. This is true for all m larger than or equal to 1. All right? So now let us try to prove this. So I'm not going to do the general proof, but I will give you just the idea of the proof. And you have to recurse the idea that I have given in order to be able to obtain a complete proof. Okay? So I have idea of the proof. So the first thing that I'm going to see is that two-step transition PDF will have the Markov property if this one-step transition PDF has the Markov property. Okay? So I will look at this. P of xk plus 2 given x0k. Okay? And I will show that this is going to be xk plus 1, P of xk plus 2 given xk only. Okay? If this is satisfied. Let us also write that. So here, assume that one-step transition PDF has the Markov property. Sorry, I need to write this once more. Given xk. Assume that we have this, then we are going to look at the two-step transition PDF. What about P of xk plus 2 given x0k? Given that this is true. So in order to be able to show that this xk plus 2 given x0k has the Markov property or not, I'm going to use the recursive formula for the transition PDFs. So I can actually divide it myself. So here I have xk plus 2 given x0k here. Okay? I can actually write that this is given like this. P of xk plus 2, and I can add here this xk plus 1 as an additional variable, and I have here x0k dxk plus 1. Okay? This is just the marginalization formula. If I have the PDF of xk plus 2 and xk plus 1, if I integrate it with respect to xk plus 1, I would end up with the PDF of xk plus 2. Okay? And then I will write the conditioning formulas. So this is going to be P of xk plus 2 given xk plus 1 x0k times P of xk plus 1 x0k. Okay? dxk plus 1. I have written this using the conditional PDF formula. So just write this conditional PDF as this PDF divided by this. Okay? And that is going to give me this PDF is equal to multiplication of these two. So now I can actually do the following. I know that this PDF, this is a one-step transition PDF somehow. It's like this. And I assume that this has this property, Pxk plus 1 given xk. So this, instead of this, I can actually write P of xk plus 1 xk. The xk plus 1 integral will still be there. Okay? And similarly, here, you see that this is nothing but, again, one-step transition probability, but instead of k plus 1, I have k plus 2. And all of the previous ones are given until x0 to xk plus 1. This is also a one-step transition PDF. As a result, it needs to satisfy this property. So we are assuming that this is true for all k. So I can here substitute k equals to k plus 1. Okay? In that case, I would see that P of xk plus 2 given x0 k plus 1 is equal to P of xk plus 2 given xk plus 1. Okay? In this property, if I substitute k equals to k plus 1, then I would obtain that property. So here I see that from this PDF, I can remove all of these past variables, x0k. I can only leave the last one. But here I'm not going to do that. So I will only remove from x0 to xk minus 1. It is actually going to make things easier, but here I can remove all of this, but really it is not. It's going to be correct in that case. But I will also keep. I want to here keep the xk as well, although it doesn't have any effect. Okay, this is xk plus 1, xk. Now, if I leave xk here, you see that the conditioning in both of these distributions would include xk. Okay, that is why I leave this one here. Really here, leaving this here or not, really it doesn't matter. Okay, that is why I can leave it here. But that is equal to, so this is going to be, this multiplication is just going to be P of xk plus 2, xk plus 1 given xk dxk plus 1. Okay? Using the conditional distribution formulas. Okay? I know that this conditional distribution is nothing but this joint distribution divided by this. As a result, here, this multiplication is nothing but this joint distribution. But then, this is a joint distribution, and then I'm trying to marginalize out xk plus 1 from this formula, which is going to give me pxk plus 2 given xk. So we see here that we have proven that two-step transition PDF, has the Markov property. If I have one-step PDFs having the Markov property. Okay? But then we can continue this logic for any step transition PDF. So if I would like to three-step transition PDFs, this is a three-step transition PDF, then I can always write this as P of xk plus 3, xk plus 2 given x0k dxk plus 2. And we see that this is going to be pxk plus 3, xk plus 2, and I would have here x0k given pxk plus 2 given x0k dxk plus 2. Okay? But then I can here know that here I can write this. I know now that two-step transition PDFs would satisfy the Markov property, meaning that instead of this, I can remove all of the previous states, given xk here. Here I have the xk plus 2, okay? And I can actually write this as pxk plus 3 given xk plus 2 is always given here. I have here x0k. These are not affecting this distribution. I can remove this. And in addition to this, I can here, since this is a one-step transition PDF, I can here add xk plus, I can here leave xk here. Okay? Sorry, I made a mistake here. So of course, I can remove here all of these x0k from here, because this is a one-step transition PDF, and I can actually remove all of the past PDFs, because we are already assuming that one-step transition PDFs would have Markov property, and here I really do not want to remove everything. Here I want to still keep xk here, all right? Because I want the conditioning in both of these distributions to have xk, okay? Then the rest is going to actually follow as follows. So then this multiplication is going to be p of xk plus 3, and I would have xk plus 2 given xk, the xk plus 2. This is because this conditional distribution is nothing but this joint distribution divided by this distribution. Okay? Therefore, this multiplication gives me the joint distribution, and then I marginalize out xk plus 2 from here, which is going to give me pxk plus 3 given xk. So you see that if I assume that one-step transition PDFs have the Markov property, then three-step transition PDFs would also have the Markov property. Okay? And this can be continued so on. Until showing that all step transition PDFs would have the Markov property for any m larger than or equal to 1. Actually, it is also possible to use here the argument of induction. So we have already shown that two-step transition PDFs have the Markov property, and then assume that the k-step transition PDFs, so not k maybe, let us say L-step transition PDFs would have the Markov property. Then by assuming that, I can show that L plus 1 step transition PDFs would have the Markov property. Okay? That would actually give us a proof by induction. So now let us see a simple example of a Gauss-Markov process, and actually the rest of the lecture is going to follow from that example. Well, the example is given as follows. xk plus 1 is equal to ak xk plus wk, where x0, w0, w1 are all independent and Gaussian. Okay? Then this process, these xk's that would be obtained by this recursion would be Gauss-Markov process. Okay? So what does that mean? We are going to have pxk plus 1 given x0k is going to be pxk plus 1 given xk for all k. All right? And here k is larger than or equal to 0. And also, we are going to have the Gaussianity. So when I look at the distribution of, or PDF of x0k, this is going to be a Gaussian distribution. Normal x0k, the means are going to be x0k bar, and the covariances would be sigma 0k. And here, what do we mean by this notation? I'm actually showing x0k as follows. xk, so xk, and the index is decreasing until 0 here. So I have this vector. This vector is, I have k plus 1 x vectors here. And if the size of each x vector is n, this is a k plus 1 times n size vector here. And the means are defined as follows. Expected value xk, I would show it as xk bar, okay? And then this x0k bar is going to be these means here actually filled into this such a vector. So I have xk bar, xk minus 1 bar, going until x0 bar, okay? It is the means of mean of the distribution here. And this vector has the same size as this one, k plus 1 times n. And what is sigma 0k? It is the covariance of this vector. Is expected value x0k minus x0k bar is mean vector, and I would have here the same thing, transpose. So then this is going to be a matrix with size k plus 1 times n times k plus 1 times n. So you can actually calculate that all of these distributions will be Gaussian with means and the covariances given like this, and we would have Markov property for such a recursion. Since we have already proven that such properties would hold for this system in the earlier chapter, I will not going to prove the Markov property nor the Gaussian property. Instead, we are going to do something very, very interesting here in this lecture. And it is going to be the following fact. We are going to see that the reverse type of property given in the example would hold. Okay? In the example, we see that such a process, such a state equation with Gaussian noises and the initial condition would give us a Gauss-Markov process. Okay? And in the rest of this lecture, we are going to see that the reverse statement would also hold. What does that mean? If we are given x0, x1 going until infinity, suppose that is a Gauss-Markov process, then we are going to see that there is a representation of this process given in that state space form. Okay? Suppose that I don't have any state space equation, but somebody gives me a Gauss-Markov process, an arbitrary Gauss-Markov process, then I can actually find a representation for that Gauss-Markov process in that form. Okay? So if somebody gives us a Gauss-Markov process, we can always find a representation of that process in this form. What does it mean? I can always find these A matrices and WK noise terms for any given Gauss-Markov process. Okay? We can find AK and WK such that xk plus 1 is equal to AK xk plus WK. The example tells us the reverse implication. Okay? If we have AK WK and if we have an equation like this, then the resulting x's would form a Gauss-Markov process. And here, in the rest of this lecture, we are going to be trying to show the reverse would also hold. If somebody gives us a Gauss-Markov process, then we can always find a representation of that process given in this form. Okay? So here I will assume that, suppose that we are given a Gauss-Markov process. Okay? Meaning that we are given x0, x1, a process given like this. Of course, in order to be able to define a Gauss-Markov process, I need to define the means and the covariances of this Gauss-Markov process. Okay? So here, we are going to have the same definitions. So if somebody talks about a Gauss-Markov process, then they should specify their means and the covariances given like this. So here, we are going to be given these mean functions, xk, and I would have this sigma k is going to show the covariance of xk, which means expected value xk minus xk bar and xk minus xk bar transpose here. We know that this is an n by n matrix if the process xk has the dimension n. And I will also assume that we know, of course, if we are given a Gaussian process, then that means that we know the covariances of any number of state elements here. If we know the joint covariance like this, then we should also know the cross covariances as well. Okay? Because each of these covariances would be formed of covariances on the diagonal blocks, and in the off-diagonal blocks, I would have cross covariances of the x elements. So we're going to know the following covariances. Sigma ij, and this is going to be the cross covariance of xi and xj. What that means is the expected value xi minus xi bar and xj minus xj bar transpose. Given a Gaussian process, we would all know these terms, because that is what should be used while defining a Gaussian process. Okay? Now we're ready to write our first theorem about this Gauss-Markov process. In this first theorem, we are only going to be using the Gaussian property. So here, the theorem only deals with a Gaussian process. Okay? But each Gaussian Markov process is at the same time a Gaussian process and a Markov process. So that means that given any Gauss-Markov process, I would actually note that it is also a Gaussian process. Okay? So the theorem would be applicable to a Gauss-Markov process as well. So now let us say that let xk in Rn, and here I have k from 0 to infinity, be a Gaussian process. So I'm only using the letter G, capital G here. I won't use a Markov property. So let us say that not necessarily Markov. Then expected value of xk plus 1 given all of the previous states here is equal to xk plus 1 bar plus, I have a joint covariance here. I have a cross covariance. It is the cross covariance of xk plus 1 with all of the previous previous states here. And I have the covariance of x0k inverse times x0k minus x0k bar. Okay? The theorem continues with where to define these quantities here. Let us look at those. Actually, I have already defined them, but here let us repeat them for the sake of completeness. Here these quantities are x0k is nothing but the augmentation of xk to x0. And we know that this is k plus 1 times n size vector. And x0k bar is the augmentation of the means of this process. x0 bar. This is also k plus 1 times n size vector. And sigma 0k is nothing but the covariance of this vector. And the size of this is xk plus 1 times n times k plus 1 times n. And finally, this cross covariance here is nothing but this. K plus 1, comma 0 to k is nothing but expected value of xk plus 1 minus, I would have xk plus 1 bar times this vector transpose, x0k minus x0k bar transpose. Okay? And what about the size of this covariance? This is a cross covariance, and I know that the size of this vector would be just n by 1. Xk plus 1 is n by 1. And the size of this vector is k plus 1 times n times 1. Okay, this is a vector, and I take the transpose. So the size of this one is 1 by k plus 1 times n, and the multiplication is going to have the dimension n by k plus 1 times n. Okay. So here I can look at this formula, this expected value of xk plus 1, given all of the previous states, would be the mean of xk plus 1 plus this cross covariance. The size of this thing is n by k plus 1 times n, okay? And this is sigma 0k inverse. I know that the size of this one is going to be k plus 1 times n by k plus 1 times n. And the size of this error here, it is the subtraction of the mean of x0k from x0k, and it is given as k plus 1 times n, okay, times by 1, okay. So you see that the multiplication here is going to give us a vector which has size n by 1, okay. And that vector is going to be added into this mean vector, and that is going to be expected value xk plus 1 given all of the past states. Okay? So now let us quite easily actually prove this theorem. Okay? Proof. We know that x0 to xk is a Gaussian process. What does that mean? Joint distribution of any number of these states would be Gaussian. Okay? But that means that, so that means that x0k is Gaussian for any k larger than or equal to 0. Okay? That means that actually x0 to k plus 1 is Gaussian. Okay? Because this is true, and I can substitute k plus 1 is equal to k, and I know this. So that means that x0 k plus 1, the distribution of this states would be a Gaussian, which mean x0 to k plus 1 bar, and covariance x0 k plus 1 sigma 0 to k plus 1. Okay? So what is x0k plus 1? x0k plus 1 here is nothing but a vector xk plus 1, xk going until x0. Okay? But we see here that this is nothing but xk plus 1 and x0k. This is my x0k, and I add just xk plus 1 to that. Okay? Then what about the mean there? This x0k plus 1 bar is nothing but xk plus 1 bar, xk bar going until x0 bar, which means that this part is just x0k bar and xk plus 1 bar. Okay? And what about the covariance? So the covariance, sigma 0k plus 1, is going to have the following structure. So I would have sigma k plus 1 here, and I would have here sigma 0k. Because xk plus 1 is formed out of xk plus 1 and x0k. Okay? So the covariance of this one is going to appear as this block, and covariance of the rest is going to appear as this block, and the off-diagonal blocks are going to be actually the cross covariances. Sigma k plus 1, cross covariance of k plus 1 with the rest. It is sigma k plus 1, comma 0 to k, and the other one, this block here, is going to be the transpose of this one. Okay? K plus 1, comma 0k transpose. Right? That means that I can write this distribution as follows. So I have xk plus 1 and x0k. This vector, this is nothing but x0 to k plus 1. This is distributed as normal. The argument of the distribution is the same as this one. And the mean is xk plus 1 bar and x0k bar. And the covariance is given by this block diagonal, this matrix in the blocked form. Okay? K plus 1, sigma 0 to k, sigma k plus 1, comma 0 to k, and sigma k plus 1, comma 0k, and I have transpose here. Okay? So all of this follows from the Gaussian property of x0k, and that is the only property given to us. Now what I would like to do is to calculate the expectation of k plus 1, xk plus 1, given all of these state values, the previous state values. Okay? I see here that xk plus 1 and the previous state values are jointly Gaussian, and their individual means are given like this, and their individual covariances are in the blocks here of the covariance matrix, and their cross covariance are given in the off-diagonal element of the off-diagonal block of the covariance matrix. So here we remember our conditional Gaussian expressions. So if I have two vectors x and y jointly Gaussian, with their means x bar and y bar, and with their covariances given as this, sigma x, sigma y, sigma xy, and sigma xy transpose here. If I have two jointly Gaussian random variables, then I can calculate expected value of x given y using the following formula. X bar, the prior mean of x bar, x plus I have the cross covariance xy times sigma y inverse times y minus y bar. Okay? So now the rest of the proof is going to follow just using this fact. Okay? So by just applying this fact to this vector here, we're going to get our result. So here, let us apply that fact to our vector. So here, expected value of xk plus 1 given x0k. So here you see that this is going to serve as our x, and this vector is going to serve as our vector y. Okay? So I have x bar here is xk plus 1 bar, plus I need to put here the cross covariance of x and y, and the cross covariance is given as this one here, sigma k plus 1 comma 0k, and then the marginal covariance of y inverse, so marginal covariance of this one inverse, which is going to be the inverse of this covariance, sigma 0k inverse times y minus expected value of y. So x0k minus expected value of x0k. Okay? So you see that this is actually what the theorem is claiming. Okay? So now so we see that this expectation, it takes the value of x0k. This expectation is nothing but the prior expected value of xk plus 1. So without even knowing these x0k, I take the expected value of this xk plus 1, and then I sum it with some correction term. These correction terms would take into account the value of these measurements, the previous state measurements. Okay? So these are x0k. So we see that we take these actual values of the previous state values and subtract the mean from them and multiply them with some gain here, and we actually correct the prior mean of these xk plus 1 with this correction term. Okay? And the gain of the correction term would be dependent on these cross covariances and the marginal covariances. Okay? So here we see something interesting. If the marginal covariance of the past states is large, if sigma 0 to k is large, then what happens is that this inverse becomes small. That means that this gain becomes small. Okay? So if these past states, they are really uncertain, if they are really uncertain, then this covariance will be large and its inverse is going to be small. In that case, the gain would be quite small, meaning that this correction will have minimal effect on this prior mean. Okay? Similarly, if the correlation between the k plus first state and the previous state, if the correlation between them is small, if the correlation was 0, for example, then this gain would be 0, so this mean, this posterior mean, would be equal to the prior mean. All right? So now, based on this expectation, we are going to define some important sequence that we are going to use in the rest of the course. Let us write definition. And in this definition, we are going to define the sequence nu k. So this is the letter nu in Greek. So it's like V. And this is going to be nu. So I will just make to one tip of it just a slight turn here. I would give some turn to it, and it's going to be the letter nu in Greek, and I would have the sequence nu k from 0 to infinity is defined as, let us write the sequence nu k defined as nu k is equal to xk plus 1 minus expected value of xk plus 1 given x0k. Okay? That is the definition of the sequence nu k here. Okay? The sequence nu k defined as this is called the innovation sequence. Is called the state innovation sequence. This state means that just we have the innovation sequence for xk. When we see the outputs of a linear system, and when we calculate the yk minus expected value yk given all of the previous outputs, we're also going to define in the future parts of this course an output innovation sequence. Okay? But this is the state innovation sequence. But here, at this part of this course, I won't make any distinction. Okay? I will just talk about the innovation sequence, and in this part of the course, it means state innovation sequence. Okay? So we define a sequence like this. Nu k is xk plus 1 itself minus its expected value given all of the past state values. Okay? So here innovation is something about novelty. So actually, I have not confirmed it, but this letter nu k is the letter given to the innovation sequence because it sounds like new. Okay, so innovation is something about newness or novelty, and we call it with a letter in Greek which sounds in Greek as new. Okay, which is about newness, right? So here, actually, this innovation name has a meaning. Meaning of innovation, the term innovation, is the new information in xk plus 1, which is not present in the past, which means in the states x0k. Okay? So in some way here, what we mean by this explanation is as follows. This expected value xk plus 1 given x0k represents the information inside xk plus 1 which is coming from all of the past states. Okay? Information in xk plus 1 coming from all of the past states. Okay? And we subtract this information from xk plus 1 itself. So then the difference, the remaining part, is the new information in xk plus 1, which is not present in these earlier states. Okay? So in some way, this expectation is a way to extract all of the information inside xk plus 1 related to these past states. Okay? So in some way, I talk about two pieces of information in xk plus 1. The first part is the information which is correlated with the past, which is also common with the past states. And the second part of the piece of information is the new information which is not present inside the past states. And that is what we call as innovation. Okay? So here we can easily write xk plus 1 as follows. So I can write this as expected value xk plus 1 given x0k plus xk plus 1 minus expected value xk plus 1 given x0k. Okay? So you see that here, these expected values cancel, and I get xk plus 1 is equal to xk plus 1, which is a correct equation. Okay? But here I see that this is expected value of xk plus 1 given x0k plus the innovation sequence, nu k. Okay? So I see that I can decompose xk plus 1 into two parts. The first part is the part of it which has common information with the past, which is represented by this expected value. And the second part is its innovation part, which contains the new information about xk plus 1, which is not present inside the past state values. Okay? So now we are going to learn a very important fact about the innovation sequence. And this is going to be given by a theorem. The innovation nu k is equal to xk plus 1 minus expected value of xk plus 1 given x0k is independent from x0k. So we here get something very, very interesting. This new information in xk plus 1, it's represented by this random variable nu k, is independent from the past state variables. All of the past state variables. And we're actually going to prove this. So the first thing that I'm going to do is actually to check what the innovation sequence would be. Innovation sequence is xk plus 1, okay, minus this expected value. But we already calculated this expected value for a Gaussian process, and it was just this: xk plus 1 bar minus k plus 1 0 to k, the cross covariance, times 0 to k inverse sigma. It is the marginal covariance inverse times x0k minus x0k bar. Okay? So this is our innovation sequence. I have taken xk plus 1 and I have subtracted this expected value from the last theorem. All right? I'm of course assuming that xk is a Gaussian process now. So then what is the expected value of the innovation process? Let us look at this. nu k bar, expected value of the innovation process, is take the expected value of all parts. This expected value of xk plus 1 is going to be xk plus 1 bar, and expected value of this thing is itself, because this is a deterministic expected value. They're going to cancel. Similarly, these covariances are deterministic. They're going to get outside, and I will take the expected value of this difference. But that is going to be 0 as well, meaning that expected value of the innovation process is exactly equal to 0. Okay? And now I will write the following. So nu k minus nu k bar, this is equal to 0, so there is no harm in me writing this one. And I will write x0k minus x0k bar here. This is a vector of size k plus 1, and I have this k plus 2 here. So k plus 2 times n, size vector. This is equal to, I will write this as a function of the following quantities: xk plus 1 minus xk plus 1 bar, and x0k minus x0k bar. This vector is nothing but, as you see, x0 to k plus 1 minus x0 to k plus 1 bar. Okay? But you see that I will be able to write this vector as a linear function of this vector. Okay? And I know that this vector is a Gaussian vector. Okay? So here I'm going to do the following. Nu k minus nu k bar is nothing but this one. So I will put here identity, and I have minus this matrix times the second partition of this vector. So I would have just these, minus sigma k plus 1, 0k, sigma 0k inverse, okay? And the second part is just, this is exactly appearing in the second partition of this vector here. So I would have 0 identity there. So we see that this vector here is just a linear function of this vector. And I know that this vector is Gaussian, and a linear function of a Gaussian vector is also Gaussian. That means that this vector is a Gaussian vector, right? Meaning that nu k and this vector x0k, they are jointly Gaussian. Okay? So I see here that nu k and the states, past states, x0k, are jointly Gaussian. Okay? That is what I obtained from this analysis. Remember that if I take a linear function of a Gaussian vector, then that should also be Gaussian. And here we have seen that this vector should be Gaussian, meaning that nu k and x0k should be jointly Gaussian. Now I will calculate the cross covariance of nu k with x0k. So this is the cross covariance of nu k with x0k. If I can show that this cross covariance is equal to 0, then I will know that nu k and x0k, they are uncorrelated Gaussian vectors, jointly Gaussian vectors. So that is going to be equal to, nu k is given to us like this. Let me write this here. Expected value, I will write nu k here, xk plus 1 bar, times, minus, I would have those complicated terms. So I have here this term, which is nu k minus nu k bar, times x0k minus x0k bar transpose. So I add this term. Now I will take the expected value. So you see here that I will multiply, so this is going to be expected value xk plus 1 minus xk plus 1 bar times this, x0k minus x0k bar transpose, minus, I will multiply this term with these terms, and then these matrices are going to get outside of the expectation. Sigma k plus 1, 0k, sigma 0k inverse times expected value x0k minus x0k bar, x0k minus x0k bar transpose. Okay? So now what is this expected value? It is sigma 0k itself. Okay? It is the covariance sigma 0k. And what about this? This is also this is actually the cross covariance of xk plus 1 with x0k. So it is this covariance. This is sigma k plus 1 comma 0k. Okay? So let us substitute these results. Sigma k plus 1 0k minus sigma k plus 1 0k sigma 0k inverse times sigma 0k. But these are multiplied to get the identity matrix, and then I subtract this matrix from this one, which is going to give me 0. Okay? 0 matrix. But that means that these nu k and x0k are uncorrelated. Nu k and x0k are uncorrelated, jointly Gaussian random vectors. Okay? But remember, when we have Gaussianity, uncorrelated implies independence as well. In general, independence always implies uncorrelatedness, but the reverse implication is only possible under the Gaussian case. But here we have the Gaussian case. That means that nu k and x0k are independent since they are jointly Gaussian. That actually completes the proof of the theorem. Okay? So we see that this innovation sequence is indeed independent from the past. So when I decompose xk plus 1 into two parts, the innovation part is actually going to be independent of all of the past information. So here I see the following. I have the innovation defined like this. So that means that xk plus 1 is nothing but expected value xk plus 1 given x0k plus the innovation nu k. Okay? So you see that xk plus 1 is composed of two parts. The part related with the past and the new part, the innovation part. And we have seen that this is actually independent from the past. Nu k is independent from the past. So here, this expectation is nothing but a function of x0k. Okay? Such an expectation is a random variable. Since the past states are not specified, such an expectation would be a random variable, and that random variable would be a function of x0k. Actually, we have calculated the formula for this expectation, and it is indeed a function of x0k. If nu k is independent with x0k, then it should also be independent with any function of x0k. That means that this part of x0k, this part of xk plus 1 should be independent with this part as well. Okay? So these two parts of the xk plus 1 would be independent from each other. So that means that innovation sequence would actually give us a way to decompose xk plus 1 into two parts, two independent parts actually. Okay? The first part is related with the past, and the second part is representing the new information in xk plus 1. And these two parts would actually be independent from each other stochastically. Okay? So here there is actually a nice interpretation of this type of property. And that interpretation is called principle of orthogonality, or the projection interpretation. So here we see that expected value xk plus 1 given x0k would be a form of projection. Okay, what does it mean? So if I have a subspace, and this subspace, let us say it is the subspace of the past state values. Okay, this is the space of x0k. Okay, and I have xk plus 1 as a vector, a random vector, which is not actually in this subspace in general. Okay? But I know that this expected value is a function of x0k. That means that this expected value is going to be inside this subspace. Okay? And actually, in some way, this expected value would be represented by a vector inside this subspace or space. x0k, because it is only a function of x0k. So then what is the innovation sequence then? The innovation sequence is the subtraction of this vector from this vector. Okay? So that is my innovation sequence. So this is our new k, the innovation. Okay? And how can I represent innovation? How can I represent stochastic independence, probabilistic independence? And it is actually some form of orthogonality. Okay? So in some way here, expected value of xk plus 1 x0k is the closest vector in the space of past state values to the vector xk plus 1. Okay? So therefore, expected value xk plus 1 given x0k is nothing but the projection of the vector xk plus 1 onto the space of x0k. So I can write it like this here. xk plus 1 given x0k is nothing but a form of projection of the vector xk plus 1 onto space of x0k. So in some way, this expectation calculates to us the closest vector in the space of x0k to the vector xk plus 1. And then, when I calculate the projection error, that projection error is the innovation vector. Okay? The projection error vector becomes orthogonal to all vectors inside this subspace. What does it mean? The projection vector becomes, the innovation vector becomes independent to all x0k and all functions of x0k. Okay? And that is, so in this case, this mu k is nothing but xk plus 1 minus expected value xk plus 1 given x0k is the projection error vector. And we know that nu k is independent with x0k, and this is nothing but principle of orthogonality in the projection theory that we have seen in the course 501. So this is principle of orthogonality, and this orthogonal sign would represent independence. Okay? So remember, projection operation is only possible when we have the concept of orthogonality in a space. And orthogonality means that in the vector space, we have a tool in order to be able to measure the angles. And the angle concept into a space is brought by the concept of inner product. Okay? So if I am talking about projection, if I am talking about orthogonality, then that means that I need an inherent definition of an inner product. Okay? And actually this is exactly the case. In probabilistic, in random variables, you can actually define some inner products. Okay? In probability and random variables, you can define an inner product, and the inner product is usually coming with an expectation operation. Okay? So if I have x and y, two random variables, then inner product of x and y is defined as expected value of x and y. Okay? So this is an inner product definition, and you can actually prove that, and this is nothing but x, y, px, y, dx, dy. And you can actually prove that by using the axioms of the inner product. You can actually prove that this type of inner product definition would actually be a valid inner product in terms of linear algebraic properties, and you can show that this would satisfy the properties of the inner product. And then you can define orthogonality with this inner product, and with this inner product, orthogonality would be in some way uncorrelatedness, equivalent to uncorrelatedness. So I can actually say that the orthogonality might represent uncorrelatedness as well. If you have Gaussianity, it is going to represent also independence. All right? So there are actually books that would use this type of interpretation, and that would prove all of its results with this type of interpretation by using linear algebra. But our book, the book that we are using, is not actually using this type of methodology. It mentions about it, but it really does not use this type of methodology to derive its algorithms or its results. But actually, by using this type of inner product definitions, and by using the projection ideas, we can define the whole theory, the whole estimation theory that we are going to see in this course. And actually, if you derive a Kalman filter, which we are going to see, using a projection type of idea, we are not going to be using that type of idea here, but if you derive a Kalman filter using a projection type of idea, then Kalman filter becomes equivalent to a Gram-Schmidt orthogonalization. Okay? So if you remember what Gram-Schmidt orthogonalization would be from the course 501, a Kalman filter is going to be nothing but the Gram-Schmidt orthogonalization idea on random vectors. Okay? So here we have proven our so I will not continue with this interpretation. It's a very, very important interpretation of what we have done or what we have seen as the innovation process here. So now we have seen the Gaussian process theory that we use to define innovation, And now we're going to consider what the Markov property would bring us on top of these things. Because remember our task. Given a Gauss-Markov process, we would like to find a representation of that Gauss-Markov process in the form of a recursive state equation. Okay? And in order to be able to find the state recursion, I need to define this AK matrix, and I need to define the process noise. All right? So here, what is going to be important to us is that at the end, we are going to use a Gauss-Markov process. Now we have seen so far what Gaussianity would bring to us. And now we are going to see what Markovianness would bring on top of this theory. So now let us write the following theorem. Let x0, x1 going until infinity be a Markov process. And here the process really does not need to be Gaussian, not necessarily Gaussian. Okay? Then expected value xk plus 1 given x0k is equal to expected value of xk plus 1 given just xk. Okay? So you see that if we have Markov property in the process, then when I calculate this expectation and when I'm trying to calculate this innovation, I really do not have to use all of the past previous states. Okay? I need to use only the last state, and that is going to be possible for a Markov process. Since we're going to use a Gauss-Markov process, we will be able to apply this one as well, this theorem as well. So now let us look at the proof. In the proof, we are going to show these expected values with different notations. So let us call this as the expected value of xk plus 1. So I will show it with xk plus 1 hat. Hat shows the expected value of xk plus 1. It is an estimate of xk plus 1 given all states from 0 to k. Okay? So I will show this expected value with this notation x hat k plus 1 given 0 to k, and I will show this one as x hat k plus 1 given just k. Okay? So now let us start with this expected value. So I have proof here. X hat k plus 1 given 0 to k is equal to, it's by definition this expected value, xk plus 1 given x0k, and an expected value is nothing but an integral with the probability distribution given like this, the xk plus 1. Okay? So I know that here the process is Markov, meaning that this distribution is equal to pxk plus 1 given only the last state. Okay? So that is equal to integral pxk plus 1 given, instead of writing all of the conditioning on all of the past state values, I know that when the process is Markov, I can remove all of the state values from 0 to k minus 1 from the density. So only xk is remaining in the conditioning. So then I have here, of course I shouldn't forget xk plus 1 here, times dxk plus 1. But this is nothing but the expected value of xk plus 1 given only xk, and this is nothing but x hat k plus 1 given k. So that completes the proof of the theorem. Okay? So now we are going to, we have seen all of the facts that we need for actually coming up with a representation of a Gauss-Markov process in this form. Okay? So now let us start with the following statement. Suppose now that we have a zero mean Gauss-Markov process. Okay? x0, x1, etc. So here we are assuming that xk bar is equal to 0. Then we can find a state space representation. Xk plus 1 is equal to AK xk plus wk for x0, x1 going until infinity as follows. Okay. So here we have written the same thing here. I have a Gauss-Markov process, and I just assumed xk bar is equal to 0 for all k. Okay? And we are stating that we can find a state space representation in this form. And what does it mean to find a state space representation in that form? We mean we can find an AK matrix and we can find a process noise definition, independent process noise definition given like that. So here, in other words, we can find AK and WK independent and Gaussian. Okay? Independent and Gaussian. So here there is just this restriction. Xk bar is equal to 0. In this statement, I assume that we have a zero mean Gaussian process. This is what the book does, but is this a loss of generality in general? So this is not actually a loss of generality. So let me write this as a remark. Remark. The setting xk bar is equal to 0 is not a loss of generality. If xk bar is not equal to 0, then we can add a deterministic input term into the system to have the representation xk plus 1 is equal to AK xk plus UK plus WK. Okay? So if xk bar is not equal to 0, we can add a deterministic system into this representation that we find. But this is also equivalent to the following. In this representation, WK turns out to be normal with zero mean and QK covariance. Okay? So here, if I have a representation of this form with a deterministic input, then I can actually write this representation as follows: AKXK plus WK, and here WK happens to be just a zero mean Gaussian noise plus this constant here, deterministic constant, that becomes a new mean, UK, for the Gaussian, and the covariance becomes the same. Okay? So here, I can edit the deterministic input based on these non-zero means, and I can take this deterministic input inside the noise term by making the noise term having a non-zero mean UK. Okay? So when we set xk bar equal to 0, we are going to find this type of system. And in that system, the process noise is going to have 0 mean. All right? When we have xk non-zero, in that case, we can add that the effect of the non-zero means as just a deterministic input UK, which would depend on those non-zero means. Okay? And then I can take these deterministic quantities UK inside my process noise, which would change my process noise from a zero mean Gaussian to a non-zero mean Gaussian, which has the mean equal to the deterministic input that we have. Okay? So but here, so I have here omega k bar is, wk bar is equal to, happens to be UK. So here I want to do this general case. I'm giving you to it as an exercise. So suppose that you have non-zero means and try to find this type of system or this type of system by following the methodology that we are going to do now. Okay? So now let us assume that this specific case. In this specific case, xk bar is equal to 0. All right? So here is what I'm going to do. I'm first going to calculate the innovation sequence for this Gauss-Markov process. For this Gauss-Markov process, I know that I can calculate an innovation. And this innovation is going to be given as xk plus 1 minus expected value xk plus 1 given x0k. I know that such an innovation would be independent with all of the past state values. All right? So this innovation definition, it is actually, we can calculate this expectation using the Gaussian process properties. Because remember, we have a Gauss-Markov process here. It is also Gaussian. All right? But we have also a Markov property. That means that I can actually simplify this expectation by removing some of the conditionings from here. So this is at the same time xk plus 1 minus expected value xk plus 1 given xk. Okay? So now you see that my innovation at the same time becomes equal to this quantity, because these two expectations would be equal, because we have also a Markov process at the same time. Okay? Now let us calculate this expectation here. Expected value xk plus 1 given xk can be calculated using the conditional Gaussian variables, because we know that we have a Gaussian process, and that means that the vector xk plus 1 xk is actually a Gaussian random vector, and I have xk plus 1 xk here, and the means are 0, 0, okay? In the general case, the means are going to be non-zero, okay? And this would give me, and also I would have a covariance, and that covariance is going to be sigma k plus 1, covariance of this, and sigma k. In the diagonal blocks, I would have the individual covariances for these states, and in the off-diagonal blocks, I would have the cross covariances. Sigma k plus 1, comma k transpose. Okay? So now I can actually calculate the expectation in the innovation. So I have let me calculate that expectation. This expectation, we have called it as x at k plus 1 given k, and that is equal to the prior mean of xk plus 1, 0, plus the cross covariance, sigma k plus 1 given k, not k, given k, comma k, times the covariance of the given condition, here xk inverse, sigma k inverse, and I have xk minus xk bar, xk minus 0. So you see that I have zeros here. That is due to the zero mean property. This is just going to turn out to be k plus 1k, sigma k inverse times xk. So we see that here, x at k plus 1 given k is equal to expected value xk plus 1 given xk, turns out to be just a linear function of xk. All right? So what is my innovation? Innovation nu k is xk plus 1 minus expected, so instead of expectation, I will just write this thing. X at k plus 1 given k, it is going to turn out to be xk plus 1 minus sigma k plus 1 comma k, sigma k inverse xk. So you see that the expectation has been simplified quite a lot. In the earlier case, we had all of the states here. Now we have only xk here, and all of the means are 0. Okay? So now here is what I'm going to do. I'm going to choose my process noise in this system as the innovation sequence. Omega nu k, okay? And this nu k is going to be defined as xk plus 1 minus sigma k inverse xk. And I will define this matrix as the matrix AK. Okay? Let us define AK as sigma k plus 1k, sigma k inverse matrix. And this is going to give me the process noise is equal to xk plus 1 minus AK xk. Okay? But this means that this xk plus 1 is nothing but AK times xk plus the process noise WK. So you see that given a Gauss-Markov process, by using its covariances, we can choose these AK, and by using its innovation sequence, we can select this process noise. Okay? I know that this process noise has 0 mean, because the innovation process would have 0 mean. Okay? But here I would also need independence. Innovation is Gaussian because xk plus 1 and xk are Gaussian, and therefore innovation is Gaussian here, with some covariance and 0 mean here. And all I need here is to show that this WK is independent from the previous WKs. Okay? Because here, what we are trying to do is that given a Gauss-Markov process, we need to find a state space representation for it, and in that state space representation, AK was found, and WK was found, and WK is definitely Gaussian, because it's a linear combination of Gaussian random variables, vectors, and the only thing that I need to show the independence of WK. Okay? Here I knew, fortunately, that WK is the innovation process, and that means that WK is independent with or from x0k. Okay? That is one of the theorems that we have seen before. And by using such a fact, can I show that wk is also independent from all of the past w sequence elements? Okay? So let us write w0. W0, by using this definition, is going to be x1 minus a0, x0. W1 is x2 minus a1, x1. So this goes on until, let me write wk minus 1. It is going to be xk minus ak minus 1, xk minus 1. So here, I see that w from 0 to k minus 1, 0 to k minus 1, this is a function of the states from 0 to k minus 1, to k, okay? This is w0 to k minus 1 is a function of states from 0 to time k. So I have a function of states x from 0 to k. But I know that wk is independent with x0k, meaning that wk is going to be independent from any function of x0k. If a random variable x is independent from a random variable y, then by the probability theory, we know that the random variable x will be independent from any random variable derived from y. So if x is independent from y, x is going to be independent from any function of y. Okay? So here I can say that wk is also independent, with w0k minus 1. Okay? That means that wk is going to be actually independent, is going to be an independent sequence of random variables. Okay? So that allows us to say that wk is white. Okay? Is an independent sequence. Okay? So you see that given a Gauss-Markov process, we could find a state space representation for it, and that state space representation has a specific name in stochastic systems. Okay? So we're going to write the definition. The representation xk plus 1 is equal to akxk plus wk for a Gauss-Markov process x0, x1 going until infinity is called the innovation representation. Innovations representation of x0, x1 going until x infinity. So at each step in this recursion, we are adding the innovation, the previous part, the part of xk plus 1 related to the past, and we add the innovation, and then we get the xk plus 1 random variable or random vector. And this representation of a Gauss-Markov process is called the innovation representation of the Gauss-Markov process. Okay? So this actually completes the Gauss-Markov process investigation that we need to do in this course. And we are going to use this type of ideas when we go into the Kalman filter topic as well. So this actually finishes also the chapter that we are covering, the chapter of the chapter 3, I think. And now, starting from the next lecture and on, we're going to see the Markov chains and the so-called controlled Markov chains. We're going to try to control the Markov chains to satisfy some optimal criterion. So we're going to see, therefore, the optimal control of stochastic systems. And after we finish the Markov chains, we're going to go back to the linear Gaussian systems once more, and we're going to see their optimal control as well. And that is going to be the theory of LQG control, linear quadratic Gaussian control. And while trying to investigate LQG control, we are going to need a form of observer, and that observer is going to turn out to be the so-called Kalman filter. Okay? That's all for this lecture. Thank you very much for watching. Bye.